Welcome everyone. Today we would like to explain our research on tooth enamel. It's KIVANC here and I would like to start with some background and introduction to hydroxyapatite. Then I will mention a few applications on hydroxyapatite and my friends will move on with previous work and strategies and mechanisms. Hydroxyapatite is widely used in various fields such as material science, biology, and archaeometry because it has the combination of unique properties such as high mechanical hardness, wear resistance, non-toxicity, and bioactivity. As a result, it is used in implant coatings, for disease diagnosis, and for the dating of architectural monuments. Our tooth contains 95% of the mineral called hydroxyapatite, and it has high mechanical hardness because of the strong directional covalent bonds in phosphate, and hydroxides will form hydrogen bonds with water, giving rise to solubility. If we want to use this unique material in our research, we can synthesize it by various techniques, or we can find different sources of it. For instance, even our bones contain hydroxyapatite, and the ions here can be exchanged with different metal ions. As a result, it is used for wastewater treatments or disease diagnosis applications. Research shows that calcium and lead in wastewater can be easily taken up by hydroxyapatite, and when this material is added into limestone, its fluorine uptake capability has been increased because of the increased surface area. And for the disease diagnosis applications, nanohydroxyapatite doped and undoped gadolinium were loaded into mouse, and it has been found that the MR imaging capability has been increased when hydroxyapatite was doped. And a relationship between the drug release capability and the pH has been found when hydroxyapatite is used. So the drug release ability at the acidic environments is greater than that in the neutral environments.
Now I'm going to introduce you how other people solve the problem. The first type is conventional chemical synthesis. Chemical precipitation is favored due to the convenient operation. Researchers synthesize the HAP nanorods through this method by adding ammonium hydroxide drop by drop into acidic HAP suspension. When pH gets to 6 to 11, the nanorods will nucleate and grow from this supersaturated solution, then following with an aging process. After getting the crystals, applies surfactant to let the HAP nanorods self-assemble on an air-water interface. They finally formed a HAP prism structure similar to the mice enamel. Hydrothermal and microemulsions are also widely used for good control of microstructures. For hydrothermal, simply mix the reagents and treat them with hydrothermal conditions. For microemulsion method, it is essential to generate microemulsions to let the crystal nucleate and grow in certain shape. These two methods are also combined to create hydrothermal microemulsion method. They generate microemulsions containing the reagents first and treat them with hydrothermal condition. Then HAP nanorods with mono-distributed sites can be obtained.
The other category, biomimetic remineralization, is generally based on template methods, including hard template methods and soft templating methods. Hard templating, in which colloidal particles, typically silica or polymer particles, act as a support for the formation of crystals on the surface, and soft templating, in which colloidal structures, for example micelles, confine crystallization, mostly in emulsion and phase separation procedures. In the template method, the normal routines is first prepare the template, then use some common synthetic approach to synthesize the target product under the function of template. Finally, remove the template. This method can effectively control the morphology of nanomaterials. The single crystal to single crystal transformation has been used by some scientists due to its ability of preserving crystal morphology. Researchers found that octa-calcium phosphate single crystals can be converted into HAP single crystals with the participation of gelatin crystals. This gives a strong indication of the OCP to HAP transformation mechanism in the mineralization of biological apatite in tooth enamel and bone.
Hi, this is Prasanna Venkatesh, and I'll be elucidating some of the strategies and mechanisms employed by Zhang Li and their group to synthesize artificial enamel. This enamel retained the full structural complexity of natural enamel by combining diverse mechanical properties such as stiffness, hardness, and flexural strength. The HAP nanowires were synthesized by the solvothermal method and then were coated with a layer of zirconium dioxide. Dual direction freezing was then applied in the presence of polyvinyl alcohol to obtain a parallel alignment of nanowires. The HAP nanowires grew on PDMS layer and then were subjected to freeze drying and mechanical compression to obtain the desired artificial enamel. So this is the SEM and TEM micrograph of HAP with and without the amorphous ZRO2 layer. It has been observed that the presence of the amorphous intergranular phase considerably influences the mechanical properties by enhancing the interface connectivity between the HAP nanowires. The AIP material, the amorphous intergranular phase ZRO2, facilitates inorganic interface connection in the artificial enamel. It has also been observed that varying the ratio of organic to inorganic nanofillers also had a profound impact on the hardness and viscoelasticity of the artificial tooth enamel. This slide illustrates some of the advantages of hydroxyapatite, which is one of the most common elements present in artificial tooth enamel. The mechanical properties of artificial tooth enamel were compared with that of artificial tooth enamel without an amorphous intergranular phase, which is ATE-NAIP, and artificial tooth enamel without an ordered microstructure, which is ATE-NOM. It was observed that the hardness, modulus, and the initial fracture toughness of artificial tooth enamel were very high owing to the parallel alignment of nanowires and as the amorphous phase promoted crack deflection at the surface. The viscoelasticity of artificial tooth enamel was also very high as the nanowire slid and dissipated considerable amount of energy upon the application of external load. In a nutshell, it could be concluded that combination of parallel HA nanowires, amorphous intergranular phase, as well as organic nanofillers could be recommended to improve the mechanical properties of the artificial enamel as it combines contrasting characteristics like high toughness, strength, hardness, and viscoelasticity. The significance of artificial enamel has grown multifold as the defensive lining of enamel doesn't repair itself. It's completely irreversible, unlike the other bones present in the human body. Further scrutiny and exploration of these materials is highly imperative to yield significant results and to make them clinically safe and commercially viable for mass production. This concludes our presentation. Have a great day. Thank you.